welcome back. I hope the break was good. I hope you're able to, get all the refreshments you need and everything. Just make yourselves at home, basically, is the way to do it. So before I asked you about this quiz, here's some code, and there's a bug in there. And I asked you if you could debug it. Well, if you have a look here, there's a little dereferencing this variable here is not needed. And instead, if we put this down here on this function, this will then allow it to work, because essentially the request was being set before on a copy, because this wasn't a pointer receiver. So the fix was to make that a pointer receiver. And now when we set this request here, it's going to be set in the original struct, not in a copy of it. And that was it. That's how that works. So congratulations to anybody that was able to get that. Our next speaker absolutely loves databases, always storing things in you never can, you know what I mean? It goes, don't you, Johan? You're storing stuff all the time.
Certainly, yes, all the time.
Yeah, you're always at it. Before we get into your talk, which will be about databases, could you tell me a little bit about Viva, the charity that you've chosen to donate your speaker swag to today?
Yeah, Viva is a charity that works to promote veganism in the UK, and it's something that's dear to me because I think animals are being mistreated in the animal industry, and it's important to me that those voices are being heard.
Great. I think it's a great choice. And is it sort of more driven by a love for animals, or is it that you really hate plants?
Yeah, plants, they can go stuff it, to be honest.
Yeah.
They really have to go, yeah.
Okay, well, without further ado, I'm going to let you do your talk. This is a journey to Postgres productivity with Go. So please do actually clap, because we will be checking at people at home. Welcome, Johan Brandhorst. Johan.
Thank you. Okay, let me share my screen. There we go. Okay, hi everyone. I'm Johan. I'm a maintainer of various open source projects, including the grpc-gateway and Improbable's grpc-web. I've contributed to the Go standard library, and I run a blog writing mainly about Go and gRPC. I just started working at Buff, where we think about protobuf so you don't have to. This is my first GopherCon EU, and it's not quite what I expected. I'm here today to talk about state and Postgres, so let's dive straight in. We're going to start with the question why. What do we mean by state management, and why do we need it? We're going to move on to talking about a few different state management solutions and discuss their various strengths and weaknesses. We're then going to dive deeper into my state management solution of choice, Postgres. Once there, we're going to explore some of the tooling available and narrow it down to the pieces I consider essential to becoming productive with Postgres. At the end of this talk, we'll all be Postgres rockstars. So why do we need all of this? State management is the source of a lot of the problems we have to deal with as programmers. If we didn't need to worry about state, we'd be able to effortlessly parallelize computation with no need for synchronization, no worrying about chronological ordering, etc. It's basically the reason why we can't have nice things. However, it's also the reason we can have some things. Facebook and Twitter wouldn't be much without the ability to share text and images, and Google would struggle to be useful if it had to search the whole internet every time you made a search. State management is, unfortunately, here to stay. So we need to store data. How do we store data? Well, we could just store things in memory. Create a struct like this, store some data in a map or slice, and you're done. Storing in memory also means it's super fast to access. But what about when we need to restart your application to update it? All of your data is lost. What about when you want to run several applications because you have a high load? They can't share memory between each other. Storing data in memory is sometimes useful, but it's not a great solution for many problems. So in-memory is out. What about just storing files on the file system? The files on the file system persist across application restarts and can be shared between processes. Problem solved. Sure, things aren't as fast as when storing data in memory anymore, but that was a compromise we had to accept. Using the file system is not a terrible idea for some problems, but it also has its shortcomings. As you can see in this snippet here, we've already had to make a decision about how to store data on the file system. What about when we want to find all users who are over a certain age, or all users whose name starts with T? This and many other problems are solved for us when we use a purpose-built data store. Generally, as a programmer, anytime you need to store something for longer than the lifetime of your application, you should turn to a data store. These are applications that have solved all the hard problems associated with persisting large amounts of data, ensuring safe concurrent access, easy access to read data, filtering of results, etc. Let's take a look at a few different types of data stores. Data stores can be broadly split into 3 categories, all with different properties and use cases. These are in-memory key-value stores, document stores, and relational databases. There are, of course, exceptions to these classifications, but we're only going to cover these 3 today. So what is a key-value store? An in-memory key-value store are typically implemented to allow quick access to small amounts of data tied to a specific key. You can think of them as a distributed Go map. They are often used as caches because of their speed, but they are not meant to hold very complex data structures and often don't support sophisticated filtering of results. They are also obviously limited to whatever the size of your machine memory is. Examples of in-memory key-value stores are memcached, written by Brad Fitzpatrick, an ex-member of the Go team, Redis, and more. Having said all of that, a key-value store may well suit your needs, whatever they are. Speaking personally as someone who has implemented sophisticated logic in Redis using their Lua engine, go nuts, but make sure you're optimizing for the right thing. I was not. Document stores typically use the file system and sit somewhere between a key-value store and relational database in terms of performance. These are usually called so-called NoSQL data stores, which means that they don't require a predefined schema to work. Basically, you insert some JSON and you've got a data store. You can insert more JSON of the same format and quickly read it out again. These data stores are normally built with large-scale deployments in mind and automatically split data amongst its servers. The compromise that some document stores make to provide high performance is that some data may be missing or incorrect. MongoDB, Couchbase, and Elasticsearch are examples of document stores. MongoDB especially has gained some fame recently for its dubious claim about data consistency. Renowned database researchers Jepsen.io had the following to say about MongoDB. MongoDB lost data and violated causality by default. I don't want to throw shade on all document stores, but don't use MongoDB if you can help it. Finally, we have relational databases. These use the file system for storing data, provide strong data guarantees, use the structured query language, aka SQL, for inserting and reading data, and are often backed by decades of development and testing. They also tend to provide so-called ACID transactions, which basically means that your data will not get corrupted if something unexpected happens while you're writing. Naturally, speed is a secondary concern after data integrity, so they are normally not as fast as document stores. Oracle, MariaDB, MySQL, Postgres, and CockroachDB are examples of relational databases. All right, with that background out of the way, let's talk business. Which data store should we use? Postgres, obviously, because that's the name of my talk. For most problems, Postgres is a great alternative. It's been around for over 20 years, it's free, it's open source, and used by thousands of companies worldwide. Importantly for us, it also has excellent Go library support. For basically anything but in-memory caches, I tend to lean on Postgres. If you need to scale your database to several machines, CockroachDB implements the same wire protocol as Postgres, so can often be used as a drop-in replacement. Postgres can be run on its own in the cloud, or you can use one of the managed Postgres solutions, which exists in pretty much every cloud provider. I like that defining the database schema makes you think about how the data fits together. It's a bit like going from writing Python to writing Go, and it can save you a lot of trouble in the long run. So how do we use Postgres with Go? Unfortunately, even after choosing a database, we're presented with a myriad of options for tooling. Should we use an ORM? Should we generate the code? What driver should we use? Let's take a quick look at some of the tools available. You've probably heard of object relational mapping, aka ORM libraries, of which there are many. These try to provide an interface to the database that doesn't require writing SQL, which is often very appealing to beginners. However, ORMs often tend to become messy when working with more complicated data structures and can lead to very inefficient queries being made to the database. Furthermore, the lack of generics in Go means it often has to sacrifice static typing. ORMs are also often unable to support all the features of the databases they abstract away, as they often naturally aim to provide a database-agnostic interface. Working with an ORM can feel a bit like magic when it works, but I recommend learning to use SQL directly. It will pay dividends in the long run. Then there are generator libraries. These will generally require you to provide some sort of markup to define your data structures. It could be SQL, it could be in the form of Go code, or maybe something else. It will then generate structs and helper functions for writing and reading data to the database. They are able to provide a type-safe interface to the database, as opposed to an ORM, but none of the generators I have seen in Go can support the range of features supported by Postgres, so it's usually a non-starter for me. Having said that, generator libraries show a lot of promise, and if you know of a good one, please let me know. All right, so we're not using an ORM, and we're not using a generator library. What tooling are we going to use? I know you didn't come along to this talk to hear about theory, so I'm going to give you my own recommendations. After years of trying libraries and methods for interacting with Postgres, I have identified 4 tools that complement each other very well, each solving a separate issue. They are PGX, Golang Migrate, Squirrel, and Docker Test. PGX is the database/SQL driver and provides database types. Golang Migrate solves the initial setup and migration of the database schema. Squirrel solves the issue of writing queries, and Docker Test helps us gain confidence in our code by letting us test against a real database in our tests. Let's take a closer look at each one. PGX is a pure Go driver for the standard library database/SQL interface that also implements its own interface to squeeze that extra bit of speed out when you need it. I tend to use the slightly slower standard library interface for compatibility. It has support for over 70 Postgres types, such as UUID, HStore, JSON, byte array, interval, and arrays. It can be used with SQL Open, but it also supports a custom type for configuration things like TLS and debug logging of queries, as can be seen in this snippet here. The logging interface logs all queries and has adapters for popular logging libraries, such as Logrus, SAP, Zerolog, and Log15. You probably don't want this turned on all the time, but it can be a great help when debugging some queries. At any time, if you need to do something that could take advantage of the extra speed offered by the custom API, such as when you want to insert a large amount of data, you can acquire a PGX con from an SQL DB, as seen in this snippet. You can then do the intensive operation while maintaining the use of the normal database/SQL interface for familiarity and compatibility elsewhere. Before we dive into the next tool, let's talk a little bit about database migrations. When I first started learning about databases, it wasn't clear to me why you would need migrations. Migrations are, in the simplest case, useful for migrating from nothing to an initial database schema and back to nothing. We're going to look at an example of this in a minute. The second use case for migration is when you have some existing data, but you need to evolve the schema, such as adding a column to an existing table or adding another table altogether, and you need to do something to the existing data, such as setting a value in the new column based on current values, or inserting a row in the new table. The third thing it can be useful for is when a planned change didn't go as well as desired, and you need to roll back the changes. My choice of migration library is Golang Migrate. It supports reading migration files from a number of sources and writing to a number of different databases. though, of course, we only care about Postgres for this example. It can run both via a command line interface or inside an application at startup. The examples we're going to look at today will be using it inside the application. Note that this means that we are tying the version of the database schema to the application, which means that you have to be careful if you're running several applications against the same database at the same time. If you're using a single client per database, it is the easiest way of managing migrations, though. First up, we have to write migration files. In the simplest case, this is just the initial database schema. If your application is small and doesn't need to change, this may be all you need. Even if you don't anticipate that you will need to migrate data in the future, I would still recommend using migrations from the start, just because they allow you to easily control the state of the database schema. The initial up migrations creates the first table or tables, and the initial down migrations is an exact inverse of that. That is, it deletes the tables again, so there's nothing in the database. This adds another benefit, which is that you can clean out the database state by just running the migrations down to 0. So let's add an up migration here that creates a single table and a down migration that deletes it again. Note the naming of the files. They need to be named so that the migrations can be ordered lexicographically. It's often accomplished by using a numbered prefix, like here. So if you added another file, you would name it 002 underscore whatever. And this syntax here is just normal SQL. Next up, we have the question of how to integrate the migrations into our application. And for that, we will use the bin data generator. If you've never heard of Go bin data before, it's basically a way of taking some files on the file system and making the content importable as a Go package. This means we no longer depend on the file system, so an application can still be shipped around as a single executable. So we can take this command here, which runs Go bin data to create the bin data file, stick it in a makefile or a Go generator directive, and then import it and use it in our migrations, like in this snippet. This reuses an existing SQL.db to do the migration to version 1, creating our table. Now that we have the database schema created, we can start thinking about writing some queries. And that's where Squirrel comes in. Ever found yourself writing a huge fmt.sprintf expression, mapping column names or dynamic data into an SQL query? I've been there. Squirrel is a query builder utilizing the builder pattern to add properties to the query. The builder pattern isn't something you see often in Go because it sacrifices static typing a lot of the time, and Squirrel is no exception. I would generally not recommend the builder pattern, but Squirrel strikes a very good balance between power and type safety. The code on the screen shows a very simple example of using Squirrel. Parameters automatically become positional parameters, which prevents SQL injection vulnerabilities. It aims to support most of the SQL standard, and this can be further extended to arbitrarily complex queries with joins, Postgres-specific suffixes, etc. This example creates a query which selects all rows from the users table which have the name Johan. We then convert it into a query string and positional variables with toSQL. Let's have a look at a few more examples. This example shows a typical insertion with Squirrel. Notice how it allows you to map from column name to value directly in a map. Notice also how we're using the dot suffix to add the Postgres extension returning, which returns the data from the new row. Also notice how we've ended up with an empty interface in this map, since we want to be able to put anything that can be used as a variable in Postgres inside of the map. SetMap can be used in both insert and update statements. Finally, we also see how Squirrel can be used to invoke the queries directly without having to use toSQL. In this example, we see how Squirrel makes conditional filtering a trivial and pleasant experience. Note how we're able to use the native time type directly when interacting with the database, and that we can easily convert a duration to a native Postgres type before handing it to Squirrel using one of the powerful types provided by PGX. Using squirrel.gt, we say that we want values with a create time strictly greater than the provided value, and using squirrel.exper allows us to add arbitrary SQL commands into our filters. Note also the use of the question mark for positional variable interpolation. And this is only a small glimpse of all that Squirrel provides. Now we've got the application up and running and talking to the database using PGX, writing migrations with Golang Migrate, and writing queries with Squirrel. But there is still one piece to the puzzle. How do we test that our code does what we want it to? There exist several solutions to testing code that interacts with the database, such as mocking the database/SQL interface, or using an interface and perform testing against that. But I'm here to tell you that neither of these solutions are adequate. Fortunately, there is a better option. What if we could test against the real database? Docker test does exactly what it says on the tin. It allows you to test against a Docker container. This allows us to run tests against a real Postgres server. It can be called from normal test code like any Go library, and it uses the Docker API under the hood, so all you need is a local Docker socket. You can configure the tests to automatically clean up containers after finishing, or leave them up to allow for debugging after tests run. It comes with a convenience function to test that a container has started, and it can support advanced use cases like uploading files to the test containers and reading the log output for debugging. It works just as well in local testing and CI, so no more need for CI-specific container configuration. The only requirement is that your CI runner has access to a local Docker socket so that it can both start containers and access them via the local network. In CI, this can mean using custom runners or using something like a Circle CI machine runner. Let's take a look at a real example in my example repo. And now I'm going to be changing my presentation to show some code. And if you want to, you can take a quick screenshot of this and clone it yourself. Everything that I've talked about so far is covered as an example in this repo. And it should come to the surprise of no one that my Postgres example repo is also a grpc server. So let's take a look. I'm going to change my presentation. Okay, so what we've got here is the initial schema migration. We saw an example of that earlier. And in this case, we're doing basically exactly the same thing as before, but we're also creating an enum here. We don't really need to worry about that. It's a little bit more fancy to show that you can do those sort of things with the PGX types. But this is just creating a normal table. And then if we jump to users.go, then here we can see that we're creating a new directory, where a directory is something that interacts with the database. It needs a URL to connect to, and it takes a loggers logger. And we can see that we're using the PGX types here to parse the config from the URL, and then setting a logger, and then using the PGX OpenDB function to create the database. And then in validate schema here, if we take a quick look, this does the migrations that we discussed before, and it's locked to version 1 because that's the version that we have. And if you wanted to add another migration here, you would add a file, regenerate the bin data file, and then set this to version 2, and it would just automatically apply both version 1 and version 2 next time it connects. And then if we scroll down here, we can see that we have some examples of Squirrel interactions. So we're inserting into the users table. We're setting the role of the user to the parameter that comes straight from the grpc server, actually. And then it does a little bit of a fancy handling here to convert to a database value type. If we take a quick look here, you can see that this type here implements the database driver.valuer and driver.scanner so that you can both read and write to it. And then we're using the suffix here to return the ID, role, and create time of the new row. And then we have a helper function here for scanning directly from a row that's returned from query row context. And we have a delete user here as well. So that, again, we're using Squirrel delete, where ID equals get ID, and we return the row that we deleted. And then we can also do some special error handling here to find if the ID that was provided was not a valid UUID. And then in the list users here, it's a little bit more interesting. We're doing a select, but we're also doing this conditional formatting, as we talked about. So you can take some time to look through this later because I'm running out of time. I want to get back to the tests. If we look at the user test here, we have a function called start database, which is a new testing helper. So you can mark it as a helper, and it will be removed from the backtraces if there's an error. And then you can see here that we're creating a Postgres URL, we're creating a pool, and setting up environment variables that will be necessary to start the Postgres container. And then we just call pool.run Postgres with the tag 13-alpine with these environment variables. And we can use these new Go 114 cleanup feature to automatically clean things up as soon as the test has finished. And then the magic is here, where we ask the Docker socket, okay, what is the IP address of the container that you just started on my local Docker socket? And we can set that to the URL host. And then there's a little bit of magic here to work around the fact that Darwin Mac has a special implementation of Docker. We're also attaching the container logs to the container when running. You can skim over this a little bit. You can see we're cleaning it up afterwards. And then down here, we have the function that automatically retries a database connection until the database has started. So you don't have to worry about the database taking some time to spin up. It's all as soon as the start database function has returned, you know that a database is running and it's online. So then we can use the start database here when creating a new directory. As you remember, the new directory takes a URL. Start database returns a URL type directly, which is the URL to the container that we just spun up. We can use the directory so here we have a couple of tests that we run in parallel. You can see we can do things like add user, delete user, and see that all of that works. And because these tests are completely independent of each other, we can both run them on the same database at the same time, which means that the tests are faster. And then in general, we have several tests here, but you can see that each one of these tests uses a separate database. So the tests can also be run in parallel because they just spin up a separate container. And again, we can use cleanup here to close our directory afterwards. So you're probably saying, okay, great. We can run tests against a container, but I've written integration tests before, and they take flipping ages to run. So I'm going to see if we can convince you that it's actually worth doing by showing you just how quickly these tests run. Oh, okay, this has to actually pull the image now because I'm on a new computer. But this is pulling the Postgres image in the background. So it's going to take a little bit longer. I'm going to rerun it in a second, and you will see just how quickly this is. It's an Alpine image. It can't take that long, can it? Okay, that took 12 seconds, and that includes pulling the image. But if I run this again now, 3.6 seconds to spin up two containers, run several integration tests against them, and then tear them down again. I think you probably have time to do that within your testing. And as you can see, this just runs Go test. You can run this in CI. As long as you have access to a Docker socket, it just works. And you're testing against a real database. So you know that it will test that all of your queries actually work, all the data is being read back, and so on. Okay, let's jump back to the presentation. Let's quickly review what we went over today. In summary, we started out by looking at state management and why we need the data stores. We learned about a few different data storage solutions, such as Redis, Elasticsearch, and Postgres. We learned about the 4 libraries I consider essential to becoming proficient with Postgres in Go: PGX, Golang Migrate, Squirrel, and Docker Test, and looked at an example that incorporated all the different tools. Putting all of it together, we become Postgres rockstars, ready to be productive with Postgres the next time we need to store some state. I hope this talk is giving you the confidence and desire to try out Postgres with Go. It's something I enjoy every time I do it. Thank you. And now I think we have time for some questions.
Hello. Thank you, Johan. Great stuff. I can't believe how fast that test ran.
Right? It surprised me as well the first time I learned about it. It's super cool because you expect it to kind of take ages to spin up this database and you'll get started, but actually it starts up really quickly.
Yeah. Was that doing the Docker thing as well?
Yeah, that was everything all in once.
Yeah, because that was going to be my question was, if you're using Docker as sort of developer environment, what's involved in that and what's the time that it has to take to kind of spin up and stuff. So I'm shocked. Does it leave those Docker images running in the background, or does it?
So that actually included deleting them as well immediately afterwards. But you can remove the pull.purge function that was being called in the helper, and you leave them up if you want to query the database afterwards.
Right, that's awesome. Huh. I'm just checking the list. I don't know about questions. Oh, someone's asking, why would you use a Docker container compared to just spinning up, like with a continuous integration, spinning up an actual instance of the database?
Yeah, so if you do that sort of thing, which I know GitHub and Circle CI supports natively, where you can say, here, I want the test to run with this container next to it. The problem is that you can't run that locally, because it requires you have to manually kind of run the container locally when you run tests. So you don't want to have to do that. That adds extra developer friction. The benefit of this is that it works both in CI and locally. You just have to run Go tests, and you don't have to worry about anything.
And I suppose all the developers can have different development machines even.
Exactly. All you need is Docker. That's the beauty.
Yeah, very cool. Well, Johan, thank you so much. That was brilliant. I'm going to now take over the screen. I think if you could stop sharing yours. I don't know how that
Okay.
works. Yeah. I just wanted to call out, there's this networking tab where you get 2 minutes and 40 seconds of time with random people. So if it's a great kind of replacement for actual conferences. So check it out. And Johan, if you want, you could go and explore there, and people have the
really
chance
cool
of running into you, which would be nice for them, wouldn't it? So we're going to have a quick break, a bit longer this time. I'll leave you with this quiz. I'm also tweeting these quizzes because the screen doesn't stay up, I know. So here's the next one. There's a bug in this code which is making it misbehave. So if you could find out what that bug is, and you can tweet at Matt Ryer. I'm going to be looking for answers there, and I'll tweet them. We are going to be back at 20 minutes to the hour, 40 minutes past this current hour. I think we should do relative time from now on, since we're all in different time zones. So yeah, we'll see you in about 10 minutes, a bit less. Thank you.